Okay.
So, good evening, everyone. Today our speaker is Dr. Christopher Germain, my advisor. He doesn't need any introduction here. Still, if you don't know him, he is an associate professor at computer science in Rice University. He joined Rice in January 2009. Before that, he was a faculty in University of Florida from 2002. His research interests span databases, data management, data mining, and statistics. He's particularly interested in the problems related to dealing with rigorous statistical analysis and algorithms to very large-scale data. He teaches 2 courses at Rice, one for the undergrad, COM 330. It's Tools and Models for Data Science. It's a very exciting new course. Another one is COM 430, that is Introduction to Databases. It's for grad and undergrad. Yeah, so that's all about Chris. Now today he is going to talk about modern tools for data science, data management, and analytics. So without further ado, it's my pleasure to welcome Chris. Stage is all yours.
Okay, thank you. So I'll actually take this opportunity to mention that I am no longer teaching COM 430. Yeah. So John Greiner is going to be teaching it, and actually there's going to be a 530, which is a totally different class. So even if you've taken 430, you can take 530, right? But the registrar can't seem to understand that there is actually like a 500 and a 400 level class that are different. Okay, so thank you very much. And so this is actually a brand new talk. I've never given it, so we'll see how it goes. And I'm going to spend about half the time just putting some of the work that we do in our group in context by going through a brief history of data management. And I think that's really important to understand where the field has come from in order to understand where it's going. Okay, so I'll start out by going all the way back to the 1950s. Right? So this is a very, very exciting time for computing. It was the first time that computers were widely available. And what I mean by that is that you might find a computer in a major research university, right? So they were actually getting out there. And people realized that programming computers was a difficult thing, right? And so in the late 50s, you had the invention of Fortran by John Backus in 1957. And then John McCarthy famously invented Lisp in 1958, but it wasn't actually implemented until later. Now, the thing that's interesting is that at this point, nobody cared about data management, right? So the impetus for Fortran was scientific applications, right? Or how we could lob missiles at the Russians. Lisp was really mathematics, right? So people like McCarthy were really interested in applying theory of computation directly into programming languages, right? But data management just wasn't on the screen of these very early inventions. And so this prompted a couple of years later the first meeting of this body called Codicil, which is very famous in data management circles. And this was a bunch of people who were not computer scientists. They were primarily engineers. Now they were also interested in besting the Russians, but they weren't going to throw missiles at them, right? They wanted to do things like there were people from NASA that attended, right? So they were interested in building rockets and winning the space race. Various people from the DoD were in attendance. And the thing that came out of these initial meetings was this wonderful read. I will let you read the title of this report. I can't believe that anyone would ever call a report something this long. But the important thing that came out of this, that was described in this report, was this language called COBOL. Now, everyone knows Lisp and they know Fortran, and there's a certain reverence for these initial languages. COBOL fell, it was right after that. But for whatever reason, COBOL does not get the same amount of reverence. Okay? And so here is a snippet from a COBOL program in case you've never seen it. The way that COBOL differs from these other languages is that it's really meant for record-at-a-time processing, right? These people that developed COBOL were interested in having files of records and being able to iterate through them and navigate through the files of records, right? And so that's exactly what the programming language is good at. I've got my picture of God giving us COBOL right there. Okay. Now, while Codicil was hard at work on these sort of initial efforts at data management, other people were as well. So people soon realized it wasn't just all science and math, and that data management was important. And so you had IBM, they came up with something that's a very well-known system called IMS, right? Stands for Information Management System. And the first time that this was used, was actually deployed, was again towards besting the Soviets. So in 1966, it was used to support the launch of the Saturn V rocket program, right? So all of the pieces of the Saturn V rocket, if you've never seen one, it's a very impressive rocket, right? These things were all stored in this database that was developed by IBM. Now the thing that's notable compared to COBOL is that IMS actually included the first serious attempt at building a data model. Right, so COBOL was just a programming language, a record-oriented programming language. But IMS actually included sort of a view of how data should be organized. And this was quite revolutionary. And so IMS, the people who worked on IMS famously came up with what we know today as the hierarchical data model. Okay? So this is actually, what they said is you should store data in trees. Okay? And so like as an example, we might have this situation where we have departments, where we have department names, supervisors, and addresses of the department. Then we have employees who are in departments. And then we have projects that are under employees. Okay, so these arrows here represent one-to-N relationships. And the idea was that when you had a query or a computation over data stored in the IMS database, you were going to navigate this tree somehow, right? It was fundamentally based off the breadth-first navigation of trees. So as an example, if I said, which employees supervised by Chris work on the Pliny project? So what I would do is I would start at the department, navigate down to all of the employees that were actually supervised by Chris, right? So I'd ask for the departments, for Chris as supervisor, navigate through all the employees, and for each employee I would check the project. And so this system actually included a special purpose data management programming language called DL1, which facilitated exactly this navigation, right? So you said get unique department with the supervisor's Chris, and then you had this until failure where you basically looped through in breadth-first fashion all of the employees associated with Chris, and then once you find an employee, you're going to loop through, or in this case, we're going to directly check where that employee is on the Pliny project. Okay, so that's how queries worked in this system. Okay. Now it turned out really quickly, people realized that this was a really crappy data management way to organize data. And the problem is that when you have many-to-many relationships, which are ubiquitous in real data, you have redundancy. Like as an example here, if you have a department which has many employees, but an employee can have many departments, then in order to associate each employee with the department that they're with, you have to repeat that employee multiple times. Does that make sense? Right? And so you're repeating age and salary and so on. And actually very early on in the theory of databases, theoreticians realized that this is a very, very bad thing. And they sought to people like Moshe sought to get rid of redundancy from databases. Okay? Actually, it's interesting that we're not really worried as database people about redundancy because of the cost in terms of storage. We're worried about redundancy in terms of the cost of inaccuracy, right? What do you do when you have the same piece of data stored twice in two different ways? Okay, so in the meantime, as IBM was working on this, you have the COBOL people, they kept going, okay? And so they published yet another report, in actually a lot of them, but another very well-known report in 1969 that was called the Codicil Data Model, which described the Codicil Data Model. Okay? Now, in contrast to the hierarchical data model, which we have here, okay, so the Codicil Data Model was actually a network. Okay? So what they did was they said, well, we don't have a hierarchy, we actually have a network. And if there's a many-to-many relationship, what we're actually going to do is stick a guy in the middle here, right, which is going to allow us to navigate either way. And so, okay, let's say I have the question, which employees supervised by Chris work on Pliny? Okay? So what I would do is I would write code, maybe it's COBOL code or another sort of code, and I can actually pick any of these nodes in the network as an entry point. Okay? Like as an example, this might make sense if there were a few employees per project, right? So what I would do is I would start with the project, I'd get the Pliny project, then I navigate up through the works, right, to find the people that work on the Pliny project. For each employee, I'm then going to check their affiliation. Okay? And when I check their affiliation, I can then see if they are supervised by Chris. Okay, so as an example, I could also write COBOL code to navigate the other way, right? I could start at the top, and this might make sense if there are a few people supervised by Chris, because I just start with Chris right away. I find the one or two people who are supervised by them, and then I work my way down and check if they're in the Pliny project. Okay? So again, the whole point of this hierarchy or this network model is I would write COBOL code and work my way through the network, trying to find the pieces, string them together that are going to tell me if this is a correct answer to the query. Okay. So people pretty soon realized that this was as bad as the network model, or as the hierarchical model. And the reason was that the code actually locks you into an access pattern, right? So we now allow for more access patterns. We can navigate in many ways. But the problem is, you spend a lot of money writing COBOL code to answer queries, right? And what if it turns out that you wrote a query that went from the top down, but you found out that you wrote it the wrong way, because it turns out Chris supervises a lot of people? Or what if you wrote your code early on when Chris didn't supervise a lot of people, and then it turns out, well, Chris hires a lot of people, now your code no longer works right, okay? So code locking you into an access pattern very early on was real. People recognize this as a bad thing, right? Because what you want is you want people to write code and have it work forever. The problem is with data-oriented code, that data changes, right? So code that you write once may not work forever. Okay, so at this point we had these, people realized there was a lot of money here. Okay, these systems were created and they sold for a lot of money. And so we had all these arguments as to whether we should have networks or hierarchies, and so these wars raged. Okay? And then really where things fundamentally changed was that there was this guy named E.F. Codd, Ted Codd, who was a researcher at IBM, who actually published internally a paper, I believe in 1968 or 69, that first described the relational model. And he subsequently published it widely in Communications of the ATM in 1970. Okay? It's actually interesting, he won the Turing Award for this work 11 years later. And it seems in this day and age unthinkable someone could win the Turing Award in 11 years. And I sort of think that is sort of indicative of how large the field has gotten, right? How things are much different now than they used to be. Okay, so the relational model. So how does it differ? Okay? So the relational model differs in that Codd basically said having links is for dumbasses. You don't want to do that. Okay? What we want instead is to have all links between these things be implicit rather than explicit. Right? We don't have explicit links that use a programmer chase. We implicitly link things up, right? So rather than having a works node in a network, I'm going to have a works for relation, which is going to just list employee names and project names. Okay? And if I want to actually traverse something or find how these things link up, I'm instead going to use a set-based calculus to just describe how I want them to link up. I do not write actually code to perform the linking. Okay? So what do I mean by that? Because I just can't overstate what a revolutionary idea this is. Okay? So queries, in Codd's view of the world, should require absolutely no navigation. Okay? So instead, Codd said that you should declaratively state what you want, and he actually came up with a language that was based off of first-order logic. Okay? So he didn't want imperative programming. He didn't want people to use COBOL to say, do this, then do this, then do this. And again, the reason was because your COBOL locks you in to a particular sort of data set that's going to work on, right? Instead, he said you should say what you want, so it's going to work for any data set, right? And so he proposed something called the relational calculus, okay? And here's an example of, there are many flavors of relational calculus. Here's an example of the relational calculus that I tend to teach in my database course that answers the question, or that computes the answer to the question, which employees supervised by Chris work on plenty. And so the fundamental difference is that I'm basically got a mathematical construction here, right? I say, I've got a set, and I want the employee names, okay? And I'm going to have a such that bar where I say such that the E that's producing the employee name is a member of the employee set, right? So this is a set-oriented calculus. And then I have an existential quantification here, where I say, and there is going to exist a WAD pair, where W is from works for, A is from affiliated with, and D is department. So the W and the A are specifying the links. And then I have a logical expression that basically tells me when all of these things, this E, the W, and the D link together correctly, right? And that totally makes sense. You're going to say where the employee name is the works for name, and the works for project name is 20, and we're going to link up the employee names with, right, with the affiliated with, and all this kind of stuff, right? So pretty simple, right? Very, very beautiful. And so at this point, so he published these ideas in like I said, so internally in IBM before 1970. And so, so the response from IBM was a big yawn. Okay, so they didn't really care. And so I actually never met Ted Codd. He's actually passed away, and he was active in the database community before my time. Okay, but I guess I'm being filmed here. Yeah. But let's just say that knowing the stories about him, he probably pushed outside of the acceptable channels to have his model be used widely, which likely included things like going to customers, maybe behind IBM's back and getting them to sort of want this thing without the consent of his bosses at IBM, okay? Which is, I guess, wholly understandable if you think that you've got a great idea and IBM's not listening to you, okay? And probably IBM was not listening for the wrong reasons. That they were pushing their IMS system, and having the relational model out there was a direct threat to IMS, right? By the way, I should still say IBM sells IMS today, right? So these systems are still around, okay? So finally, because in at least no small degree to the pressure that customers put on IBM, that Codd caused them to put on IBM, IBM began a very, very famous research project in 1974 called SystemR, where they built the first relational database system, okay? Hugely influential. They sort of developed an architecture that we still use today, that all modern databases use today. Interestingly though, so they built this thing and they were really content to write a bunch of papers on it and get all this stuff out in the public domain. And they were pretty slow, right? Because again, they had their commercial system. This was part of their, I forgot what they call it, but IBM had this like grandiose name for it, like their Future Visions project or something, right? So that's sort of how they saw this thing. Meanwhile, there was this guy named Larry Ellison, right? Who was eagerly reading all these papers. And his point of view was, the relational model is a great idea. I don't really care if we don't know how to do it right? I'm actually just going to build a system, I'll call it a relational system, and even if I don't have all the functionality and I don't follow Codd's vision exactly, we'll get there eventually. And so his big thing was, I'm going to jump everyone, I'm going to get a relational database system out there. Okay? And so he actually first put the Oracle Relational Database Management System on the market in 1979, a year before IBM. And I don't know that it's a total coincidence that you can actually look up the historical numbers, that IBM's market capitalization in 1980, when they first had their product cap, was 116 billion in inflation-adjusted dollars. It's now 147 billion, right? Oracle was about zero, and it grew to 161 billion, largely on the strength of the Oracle Relational Database Management System, okay? I actually point out that Oracle was terrible for a long time. It's actually a great system now, but it's absolutely terrible. There was a famous story. There was this guy named David DeWitt at Wisconsin. I will mention his name again later. He very famously published an extensive benchmark of the available systems shortly after this. And he had figures that made Oracle look terrible. And so Larry Ellison actually went and tried to get him fired from Wisconsin. And unfortunately, he didn't understand how tenure worked, right?
Probably still does it.
Yeah, and you know, if you know the stories about, I've never met the guy, if you know the stories about him, this is probably in keeping with at least the stories of his personality. And actually this caused, the result of this benchmark, caused now that all commercial systems have these, or most of them have they expressly prohibit in their licensing publishing benchmarking results. So you actually see in database literature and scientific literature, people will call things like System X, right, so that they don't violate the licensing agreements.
So Chris, an interesting other thing that happened in that time frame was the move from mainframes to departmental servers.
Mm-hmm.
Because if Oracle's only channel was the mainframe, they wouldn't really be able to get a foothold over there. But
Exactly, that's a great point. Yeah, so there were the other shifts in the technology industry.
Right,
Yeah, that really aided this. Okay, so this actually begat 25 years of dominance, okay, for relational databases, okay? So other ideas come and go, but relational dominates. So I've actually got, so here's relational systems as Hercules, right, slaying the Hydra, okay? So here's another one of Hercules' foes, which he slayed these killer birds, right? Okay, so one of the foes that people were excited about in the 1980s was object-oriented databases. So for a while, people were sure that this was going to get rid of the relational Hercules. Okay? So the idea in object-oriented databases was that in the 1980s, people sort of first discovered object-oriented programming. Now that's not totally correct, because object-oriented ideas and actually implementations had been around for a long time. But the 1980s saw these things finally get a foothold. Okay? And so people said, oh wow, we're all excited about object-oriented programming. It makes sense to essentially have persistence and add it to programming languages, right? So I'm going to take my favorite OO language and make objects persistent. And so I can do then everything that the database does, right? So I might have works for project and employee, and then what I'm going to do is have a class project, a class employee, and then rather than having a works for, I'll have something like an emp list inside of the project, right? Where this is an emp list, just basically a linked list. And then the way that I get all the employees who work on the project is I find the project and then just navigate through in the host language, right? So this was sort of as C++ was becoming popular. And so people imagined persistent C++ where you would essentially write C++ code, not SQL, not any of the other competing languages out there. You'd write native C++ code to navigate these objects. Okay? And the thing is actually that this never caught on. Okay? So I think there are two reasons for this. And that is, number one, that the simple structures from OO programming available in the 1980s were easy to represent in the relational model. I mean, people essentially had ideas like this, right? And these look a lot like records, right? So people ask, like, well, what in the hell am I getting from this I'm not getting from a relational system, okay? Modern OO languages have support for generics, right, or templates. And those ideas were around in the 80s, but they were not widely known, right? And so, yeah, so we just didn't, it wasn't clear what you got from an OO database, okay? The other thing was that the vision of programming only in a host language meant that we lost the declarative query language, okay? People made the argument that, wait a second, isn't what Chris just described a lot like going back to Codicil, right? I'm navigating links, okay? And so these were sort of killer arguments against OO databases. Okay, so after OO databases, the next major challenger was XML databases, okay? So everyone knows what XML is. XML is a huge technology. And XML first came into existence, right, to deal with this problem of data interchange. Right? Everyone's got data sets, and they want to send them back and forth. And before XML, everyone had different formats, right? You could have this CSV format, you could have Excel, you could have whatever it is, right? Everyone had proprietary formats. And it was a big mess, right? So you had to write converters or whatever, you get a file from someone, you wouldn't know what it is. And so the idea was you have this self-describing format. And so people had the great idea that, hey, we can actually turn this into a database. Okay, and there was Hercules' famous bear hug. Okay. And you know, XML essentially has like this semi-structured model. And so here actually is an XML quote-unquote database that stores some information about the labors of Hercules. Okay. And so people said, hey, this is great. It's this nice semi-structured data model. It's self-describing. And they actually even came up with, they learned the lessons of the depth of the object-oriented model and actually came up with a pretty nice declarative query language called XQuery. That could be used to navigate documents like this, okay? And so the thing is that XML, of course, is with us today. So it's a big deal, right? Successful for data interchange. But the XML database model never caught on, okay? You'll find different arguments as to why that is, okay? But I think a lot of them come down to that it actually inherited a lot of the quirks of the hierarchical model, okay? So it's oftentimes unclear how to organize your data into hierarchies, right, when you have these many-to-many relationships. And in practice, XML has some similar problems. Okay, so this was 25 years of dominance, right, from around 1980 up until the mid-2000s. Okay, and then in, I guess, 2004 was the OSDI paper and MapReduce from Google. Okay? And this really changed a lot. So this was the first time that the relational model had a serious competitor. Although it's interesting that MapReduce, as we'll see, is not a data model. Okay, so if you don't know anything about MapReduce, okay, I'm assuming maybe 60% of the room does know MapReduce. Okay? But the idea in MapReduce is that we're going to have a large file of key value pairs. Okay? So I've got here, let's say that, imagine I had 57 trillion records that showed for all the classes that Swarat and me and Luai have taught. Okay? And because we've taught a lot of classes, right? And so what we got is for like Comp 330, okay, these are the final scores that were given out. Okay? Yeah, you'll see that like Luai actually managed to get even a negative grade. It's not just going to give them a 0 in their GPA, right? It's going to lower their GPA. So So we have this huge file of grades, and we want to compute an average grade per professor. Okay? And so what happens in MapReduce is that the user supplies some code to parse the input into a bunch of key value pairs. Okay? And the input is, so the system, the MapReduce system, uses that code to break the input up into many sequences of pairs. So what happened in this case is I had 6 pairs, right? And the MapReduce software decided to break it up into 3 sequences of 2 pairs. So then what happens is that the user is going to supply a map code, okay? And what that means is basically, this is just an arbitrary code that takes the key value pair and runs some transformation on it, okay? Now in this particular case, that transformation is that I'm going to take the instructor, right, leave that unchanged, but I'm going to sum up and count the number of individual scores, okay? Right? Okay, so the output of the map phase then is a bunch of records, right? So the number of records generally, though not always, is going to correspond to the number of input records for the map phase. And then what happens is we have a shuffle, okay? And so the shuffle essentially all it does is, and again this could be happening in a huge compute cluster, right, at very large scale. I'm going to go ahead and combine all of the records with the same key. So they actually get a key followed by a list of values, right? So in the example of Germain, I'm going to have all of the totals and counts for all of the classes that Germain has taught. Okay, so that's the shuffle phase. And then the reduce phase is that a user supplied, basically a user supplied reduce code is going to process these groups. And now in this particular case, like all this does is, right, it computes an average. So it's going to sum up all the totals, sum up all the counts, and divide, right? So you see Luai's average is much lower. Okay, so it came from Google, right? And so immediately everyone, Google's awesome, and so immediately everyone took notice of this. And very, very soon, right, actually from someone who's now a database professor at University of Michigan, there was this very well-known open source project that was started called Hadoop, an open source implementation of MapReduce. So it was a big deal very, very quickly. But it turns out that some database people who had been through all of these battles and from the very beginning, right, they were very underwhelmed, right? So famously, Stonebreaker, who's now actually the most recent Turing Award winner, okay, and DeWitt, they wrote this blog post, right? So it was actually in support of a company that they had started, which has since been sold for a lot of money, arguing why these systems, why MapReduce systems didn't really make any sense, okay? And what it came down to is that they said that the performance is terrible, okay? And the reason for this that they gave, very convincingly actually, was that the MapReduce framework essentially had no control over things like data storage format and especially schema. It was schemaless. So you're wasting all this time and effort like reparsing the data, reprocessing it every time you're doing anything, okay? So they said the performance is terrible. And they also wrote a very widely known referenced paper a few years later where they showed that the performance was terrible, okay? But I think that they missed the point, and I think they would probably even agree.
Did Google try to fire them?
What's that?
Did Google try to fire them?
No. Yeah. And I'm being filmed, I won't say anything.
Sorry.
Yeah, so I feel comfortable saying this, that they missed the point. And those guys would probably even agree, at least to an extent, that they missed the point. Okay? People actually accepted the poor performance. They didn't really care about it, because what they got for this was schema never. Okay? It turns out people are pretty annoyed a lot of the time by having to shove data into schemas. And the reason for that is they might get performance, they might make it really easy to write, that might make it really easy to write SQL code later, but it's a lot of time and effort to shove everything into a schema. Okay? And so they liked that. That was great, right? So this was one of the big reasons for the widespread, very quick acceptance of MapReduce. The other reason was that people liked not having to intermix SQL and other languages, right? So SQL is a great language, but anytime you try to mix two languages together, which you necessarily want to do when you're doing data processing, it creates a lot of havoc. And the nice thing about MapReduce, like Hadoop, is entirely Java. So you just write Java, right? There's not SQL mixed with Java, okay? This is especially important for things like machine learning and data mining, right? Where you want to use external libraries, okay? So you might want fast matrix packages, okay? Well, actually doing that in Java causes other problems, but it's still nice to not have to deal with an SQL to whatever bridge. Okay, so is this the end for relation? Okay, so we've got Hercules on this funeral pyre. Okay. Well, it turns out, right, that people thought so for a while. There were some people who thought it was going to be the death of relational. Okay, we even coined this term NoSQL, which meant originally no SQL. We hate SQL, but now it means not only SQL, right? So people sort of accepted that all these things can coexist together. And one of the things that's coexisting more successfully than some of the other things is this thing called Spark. Okay. So Spark is essentially a rethinking of MapReduce that gives you not only MapReduce, but dozens of other bulk operations, including a lot of operations that databases provide, right? So like as an example, a relational join is famously difficult to implement in MapReduce, and so Spark provides this as a bulk operation, okay? So why is Spark so popular? Actually, I think a lot of people now think that, in a couple of years, no one's going to be writing Hadoop MapReduce code. Everyone will be using Spark instead, okay? Well, I think first and foremost, my opinion is that it just has a really beautiful programming interface. Okay? So largely aided by its initial use of Scala. Okay? And then they actually went on to Python. So here's the Python example. And so it turns out that it's really, really pretty to use things like lambdas in this context. Okay? So we've got an example of just a couple of actually complete Spark codes here. So one is essentially doing a MapReduce job. Okay, in Python using lambdas. So I'll let you puzzle over that. But essentially I'm basically just parsing a file here. I'm not. I actually stole this code from the Spark website. Okay. But basically all we're doing is we're parsing an input file and then counting the number of occurrences of each word in the file. Okay. This is actually a data mining computation here where we are doing a gradient descent operation. Okay. So repeatedly what we're doing is essentially a MapReduce that is computing a gradient update. Right? And so we've got a statistical model. In this case, this is a logistic regression, right? We're repeatedly computing the gradient, updating the model, and so on, right, until convergence. Okay. So what the Spark people will say is that we have these cool things called RDDs, okay, which are essentially like a fancy data caching framework. I happen to think this is probably less important than the beauty of the programming interface that they came up with. But this is also important, okay? So one thing that Spark's really good at is caching data, right? So this operation, this thing right here is iterative in the sense that I'm making repeated passes over the data. With MapReduce, this requires like getting this huge freight train running multiple times to read in the data again and again. Whereas in the case of Spark, you read it once and then it's just processed in memory. Okay, so this is, it's really widely used now in a very short time frame. Okay. So now I'm going to talk a little bit about some of the stuff that I work on, okay? And, so my view is that if you're going to do work in data management, you're going to do research in this area, okay? When you close your eyes, you got to have a picture of sort of everything that's been done, right? The way all this stuff fits together, because there really is a long history in data management. I would say it's probably sort of as long and rich as any other area except for maybe PL. Okay. Actually, I didn't mean that as a joke. Actually meant that for me. But I guess it sounds funny.
So your videotape saying PL is richer than database.
He said older.
He said richer.
And he said maybe.
Actually, I don't know that that's actually a good thing. Because what I meant by that was that in data management, right, we've seen all these like very, very different ideas come and go, right? A lot of moving back and forth, okay? And I think PL is the same way, right? We see wild swings. Other areas like core systems, okay? So I guess like our core systems people like Rixner aren't here, or Alan, so I can say bad stuff. But a lot of those ideas were developed once a very long time ago and have not really changed much in a long time. Okay, so one of the things that I've been working on for the last few years is this system called SimSQL, okay? Sort of fits into this old data management ecosystem, okay? And the goal in SimSQL is to make this ubiquitous workflow easier, okay? So if you're a statistician, or especially a machine learning person, okay? What you spend a lot of time doing is first doing a lot of math, okay? And then what you do is you prototype that math in MATLAB, okay? And most machine learning people stop there, okay? Because if you look at the history of machine learning, they were for a long time not concerned with big data sets, right? People publish papers with 200 data points, okay? But that's of course changed in the current era of big data. And so people are now interested in going an extra step, right? And getting these models that they might have prototyped in MATLAB running on 5,000 machines on something like Amazon. Okay. So I guess a question that many people would ask is, well, isn't that what Spark's for? Okay, isn't it just as easy, like didn't you just give me an example of a Spark code that can actually run pretty nicely on 1,000 machines, okay? And sometimes I will say that something like Spark is actually a very good tool. Okay, so sometimes it's easy, but sometimes it's not. Okay? So the problem is that the reality, whatever the Spark people will tell you, okay, the reality is that you have situations where someone starts with math. Okay? So here we actually have math that describes a Markov chain for a very well-known Bayesian algorithm called the Bayesian lasso. Okay? So this is actually a very complete mathematical specification for that algorithm. Essentially what's going to happen is that we want to iteratively do steps 1, 2, and 3, 1, 2, and 3, and so on until convergence. Okay? So what happens in practice, right, is that, getting this to work in MATLAB is like hours or maybe a day, okay? Because it's that simple, right? But to get to this last step there, in practice, people they essentially turn into a human compiler, okay? And the fact is, I've seen people in my group do it, okay? So these are PhD students at Rice who are certainly smarter than the average data scientist out there. It takes them months to actually get this to work on something like Spark, okay? You end up, essentially, because the problem is that this math has many, many, many different Spark implementations. You have all kinds of choices. You have to choose how to represent the data. You have to choose how to distribute the data. You have to choose how to, what operations to use, how to put them together, what to cache, what not to cache, okay? And so, people, like I said, who may or may not be in this room right now, have spent months doing this, okay? And so it's just not that easy. Okay. And so when you look at it this way, it actually seems like a job for a database. So I made sort of a big deal before about how databases, like Codd's ideal was that you did not say how to do a computation. You mathematically specified it. And hey, this looks a lot like a mathematical specification, right? So the question we're interested in asking is, can we apply these basic ideas that have been around for a long time to compile not just SQL or relational calculus, not just something logical, but something that's statistical or mathematical, okay? And there are a lot of reasons that this might make sense, right? So the data are structured in this case, okay? So that math that I gave is operating on things like vectors and matrices, okay? So all kinds of reasons, right? Data are good, or databases are really good at this sort of plan generation from abstract specifications. That's exactly what they do, okay? They automatically consider data size and layout. As I said, the problem with the network model was that your code locked you into a particular data set, right? Databases for a long time have automatically changed to adapt to data sets, okay? And so the question we're interested in asking is, can we sort of have that last step go down from months to another day, right? Make it just as easy to do the last step as it is to do the MATLAB. Okay, and so our goal, right, is to start with a program that looks a lot like the math, okay? And this is an actual program that a graduated PhD student wrote a compiler for, okay? This is a language called Buds, and it's a program that actually is entirely equivalent to the math from the last couple of slides, okay? So it basically specifies declaratively how to compute the Markov chain from the last few slides. Okay, so what our system does is then take this thing and compile it into SQL, or something that's not totally SQL, but a lot like SQL, okay? And then we use standard database techniques to actually optimize this SQL and execute it on a large cluster, okay? Databases don't have the same problems with crashing due to bad code or bad data layout that something like Spark does, right? So Spark's model is put it more on the programmer, okay? Databases used to, right, in the early days of Oracle, that's what, it was bad, right? But now these systems are pretty good at doing this automatically. Okay, so like the high-level workflow that we're working on, right, is just like I said, we take a Buds program, we compile and optimize it, do an SQL program, and then we're going to run in the SQL and get the result, okay? So the research questions we've been looking at for the last couple of years have been, so number one is, how does SQL need to change, okay? What is it in SQL that we might need to add in order to make it a reasonable target for something like Buds, okay? Second question is how to compile a super high-level language like Buds, down to SQL. I mean, the problem with something like BUDS is that there aren't even any data types, okay? So BUDS doesn't say anything about how to lay out data. That has to be automatically generated, right? And then third, because we're making changes here, the question is, how does the database server itself need to change internally? Okay, and so really, like I said, so we've done work on this part, but the SimSQL system I mentioned a minute ago is really focused on this. Okay, so the question is, how does SQL need to change and what are the internals? Okay, and so this is something we've been working on for a long time, right? Yeah, so the things that we need to change or that we've added to it are better support for recursion. We have fancier table functions in there, these things called VG function. One thing we've been working on is native support for vectors and matrices because these are so fundamental to mathematical computations, and they're badly supported in current relational systems. Okay, support for huge query plans because these are big computations, right? They're iterative, so they might have thousands of operations. Then we have to actually implement a few new operations under the hood. Okay, so the status of this project is that we had something that was reasonably functional as of 2013. Okay, it's still the source of active ongoing research. Our system has about 150,000 lines of code. It's got a full query optimizer, which is actually written in Prolog. It works, it's got a distributed implementation. I think the largest thing we tested on is around 300 machines. Yeah, so it's written in Java, so C++ and Prolog. Okay, so just really quickly, so how well does this work, right? So it's been around for a while, so we've done a lot of benchmarking, okay? And so here's just looking at SimSQL, not the BUDS part, okay? So here's a comparison what we're doing is trying to learn a statistical model called latent Dirichlet allocation. So this is a very standard benchmark, okay? It's relatively, so it's a widely used model, but it's not simple. It's certainly not as simple as something like logistic regression that you can implement in Spark in a few lines of code, okay? And so this project where we did all this benchmarking actually ended about a year ago. And so what we did was to implement what we call the super vertex implementation of LDA. This is a pretty carefully designed implementation that's optimized for performance. We implemented it on top of a bunch of platforms. So these are some graph-based analytics platforms, Giraffe and GraphLab. We implemented on Spark using Python and then on top of SimSQL. Okay, so you can see that the lines of code are radically different. Okay, you know, even though this is 220 lines of code, getting this to work right is still months. Okay, and then we did some experiments where we ran this thing on 5 machines, 20 machines, and 100 machines, and scaled up the data set accordingly. I think on 100 machines. So this is for text mining. Okay, this particular algorithm. And I think that this size is 250 million documents on 100 machines, okay? And what's listed here is time per iteration, okay? So this is an iterative algorithm. And so we would need maybe 100 iterations, okay? This is initialization time over here, and then this one is the per iteration time. So we're talking about 100 hours on 100 machines to do the complete computation, okay? And so you look and you actually find that SimSQL, okay, does pretty well, okay, or at least as well as the other systems, right? Even though it's really we're specifying things in a very high-level database-oriented way. The interesting thing is actually that Spark does quite poorly, okay, in comparison. Now one might wonder if this is just related to the fact we're using Python, because Spark is actually running on the JVM, and so that can be kind of a nasty thing to deal with. And so we've actually got a Spark job implementation, and while it's a lot faster, okay, it's actually, we could never make it run, or Shangyu, who's, I don't know if he's here, could never make it run on 100 machines. I guess Shangyu and the guy who's graduated, okay? So SimSQL is pretty competitive. Now the thing I want to point out is that this is a prototype system. It's not meant to be used like in production, okay? I would say that our numbers are 1/10 what you would get if you built this functionality into a real database system. Okay, so that's one thing to keep in mind, right? That you could probably cut our times by a factor of 10 if this were running on Oracle. Yes.
How did you generate the SimSQL? Did it come from the BUDS, or did you do that directly?
Actually, in this case, this is hand-coded SimSQL. So I'm going to give an example from. Yeah. So, great question. Okay. So here's actually an example where we did LDA the same model. Okay. And we tried several things. These are all SimSQL times, okay? But what we did was we first did naive SQL, okay? And it turns out it was 14 hours. This is actually a different setup, more documents per node, okay? So we did naive SQL, right, which is a not smart implementation, so that was 14 hours per iteration. We did this is similar to the special one we did in the last slide, and so we cut this out into 4 hours per iteration. Okay, so this 4 is roughly the same as the 1 hour from last time. This row's doing the same thing, okay? So this is Buds using essentially a stupid compilation, okay? Was roughly the same time as the stupid SQL, okay? But the interesting thing is it turns out that the Buds optimizer was able to find a particular SQL for this that was 1/8 of the running time here, okay? So actually in the end, right, assuming we never actually did with this data set, this last computation, right? But one could expect that these times would be cut down by 1/8 actually had Buds been used. So Buds actually did better than the human SQL. And for certain reasons, that's not surprising. Okay, it's just, yeah. Okay, so I've got about 5 minutes left, so I'm going to go really quickly through another active project that we have, okay, which is the Plenty database system. Okay. Yeah, so Swarad actually talked about this briefly in his talk last week. Okay. So earlier in this talk, I argued that back in the day, it was unclear why host languages were better than database records, right? When essentially all the examples people came up with looked a lot like records anyway, okay? And this is one of the things that doomed object-oriented databases, okay? But I would say the argument is harder to make now. So I just went through the mental exercise of sitting down and asking, what would I want to store with a document, one of those 250 million documents? In the ideal case, if I were sitting down and just designing the best LDA computation from a programmer's point of view that I possibly could, what would I want to store? And actually come up with something that's pretty complicated. I have a couple of arrays, but then I have this actual data structure here that's storing this weird matrix type thing, okay? That's a map from tuples of integer to integer to vectors that are holding tuples, okay? So it's quite a complicated structure, okay? Then I've got another map here that's going to give me some topic preference, so again, some more other metadata about this particular document, okay? So this is what I would ideally like to store. And I'm going to make the argument that nobody in 1985 would have thought of writing something like this, right? Because although generics did exist, right, so they were around, I think Ada had them at that time, right? They were just not widely understood. Sort of?
It sort of is.
Okay. So I think actually things have evolved where databases are still databases. Relational databases don't have a lot in terms of object support. But object-oriented languages are just, actually no one's really object-oriented, right? Sort of programming languages in general have fancy bells and whistles that people want to use, like generics. Okay? So another example that just comes up in the Plenty project would be that I might, so Plenty, as you know, is a project, it's a data mining project essentially, right? We're trying to mine all the world's code to help programmers, okay? Combining formal methods with statistical methods. And so it might make a lot of sense to have a feature that we extract from a piece of code that's a data dependency graph, okay? And a very reasonable representation for this is I have some sort of header information. I then have a map from integers to node info, right? That's essentially giving the nodes in this graph, okay? And then I have another map from integer to integer, right? These are node IDs that's telling what the edges of the graph are, okay? So again, this is just a very simple example, but it's something that doesn't fit nicely into a record, right? It's an example where a host language makes a lot more sense, okay? Now, if we want this, what options do we actually have, okay? So relational databases, not a good fit, we've just gone through that, okay? So object-oriented databases, well, they don't really exist, but there are things that are essentially object-oriented databases that do exist, and these are called graph databases now, okay? These are not meant for analytics, right? So something like Neo4j or Titan, they are better in a sense because they give you some declarative interfaces than the classical like OO databases, but they're really, really similar. You would not want to do large-scale analytic computations like we've been talking about on one of these systems, okay? Then you have these document-oriented databases, right, that might store like XML or, something like that, right? And MongoDB is an example of this. But this is, again, it's not a good fit here, right? It's not meant for analytics, okay? So what about MapReduce or Spark? Okay, so these things actually support very nicely host language objects, right? So you can put Java objects in a MapReduce computation, no problem. They're meant for analytics. But I'm going to argue, and this is actually one of the reasons that we decided to build our own database from scratch, is that these things are too slow. Okay, and I'm arguing very quickly because we're running out of time. Okay, and so the fundamental problem is these are not database systems. Okay, they have this big stack that they live on top of. So let's talk about, like, let's say I have this class data dependency graph, and I actually want to create one of these objects and store it in the system using Spark. Okay, so I'm doing a Spark computation. I need to create and actually store one of these things on like a hard disk, a storage medium. Okay, so what I have to do is first the platform is going to have to go to the language runtime, like the JVM, and ask for a bunch of little bits of RAM. I don't mean bits as in the 0, 1. I mean pieces of RAM, because it's going to have to figure out, that data dependency graph has a lot of pieces in it, right, that needs to objectify. And so it's going to have to get all the RAM for all those little objects in there. Right? So the next thing is that probably in response to this, the runtime's going to have to perform some garbage collection if it's not already done it. Allocate the RAM, then it's going to give the result back. Now this guy, what he's going to do when he gets that back, right, the actual then code here is going to actually fill the object up. But then, stupidly, it's going to serialize it a second later, right? Which means it's actually going to have to take the unflat object and then flatten it, right, after just doing garbage collection to be able to allocate it. And then it's going to send it to storage, right? Now it's actually going to do this over a socket. Okay? And then the storage system again moves the data, it's going to write it to hardware. Okay? So we have layers upon layers. We had at least 4 copies, okay? And in practice, that's probably more. It's actually exceedingly difficult to figure out what in the hell happens with something like an object as it moves through a system like this, because all the layers. And then plus you've got things like the allocations and garbage collection, which are happening inside of the JVM. Okay? Now retrieval is just as bad. Okay, so I'll go through that. Okay? So you've got at least 4 copies and then the same thing. Okay? Now, yeah, so to a database designer, right, they're going to be like, no, that's just not the right way to do things. Okay? Actually, I'll just say that for a long time, database people didn't accept that databases should run on anything other than bare hardware, right? They said, don't give us a file system, don't give us an OS. The OS people don't know how to design these things. Okay? We just want bare metal. Okay? And some database people still feel that way. Okay, so the database way of dealing with this would be that to create and store an object, all you do is you have basically a page of RAM, okay, that's stored in the system buffer cache. And you take that object and write it there. There's no allocations, you just write the thing, right, to that page. And then later on, this guy will eventually get swapped out, right? Maybe you have an LRU or other replacement policy gets written back. So there's not the 4 copies or whatever. You wrote it to this page, and then eventually it goes to disk. That's all there is, right? Okay. Retrieving an object is even easier because all you do is you have your page, okay? You basically have the OS go from disk right on the page. It's there, right? I don't objectify anything, right? There's none of that because the system understands how to interpret what's on the page, okay? Much, 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 much faster, okay? So this leads us to the PDB system, right? Which I will just go through all this stuff, but essentially what PDB has is, our idea here is to make this essentially like a database, right? We don't have objects, but rather than having them be managed by something like a programming language runtime, the system itself manages them. The objects are actually allocated directly onto the pages where they're going to be written. We don't have things like garbage collection happening, right? We're essentially going to use the database way of allocating these things directly onto where they're going to be stored, right? We don't have these layers. We skip all this stuff, okay? So I won't talk about how queries go, but basically, queries in PDB there's no SQL, right? Our initial language is C++, although we're successful, we'll move beyond that. But basically, our C++ in a lot of ways lends itself to Kaut's relational calculus, okay? The nice thing though is that because it's C++, you for free get all the support that you would have in C for things like native vectors and matrices and all that kind of stuff, okay? Okay, yeah, so this supports complex analytics. Here's actually a skeleton of the LPA computation that's coded up in C++, okay? So the question is, how far are we, okay? Well, we're working on it, okay? So not much on PDB is actually working yet. We do have a prototype that people are using in the Plenty project. But the first real ability to do distributed queries will be sometime soon, maybe by the end of next month. And then the first real version where we can do some more complicated stuff will probably be ready by March. Okay, and so that's it. Any questions?
Yeah, you can go ahead and ask some questions.
Could you just say something about how you deal with pointers in these host objects in PDB?
Yeah, so great question, okay? So the guy who's doing that is sitting right in the front row right there.
It's difficult.
Yeah.
Yeah,
I mean,
a lot of water under that bridge in the past. I just wondered what you'd come down to.
I mean, I guess what you should ask him, but my short answer is that we actually use, since we're first using C++, we hide a lot of that in C++.
Yeah.
So to the programmer, it looks like they're dereferencing a pointer,
Yeah.
but we're actually catching that and doing our own thing.
Yeah, I got you. Thank you.
I was curious about the workflow. So the idea is you start in Buds and it produces SQL, and then the SQL works on your PDB system. Is that the way?
No, this is, yeah, it works on SimSQL. Although there's actually no reason that we couldn't move over to PDB if we wanted to, right? But yeah, so the workflow is you write your Buds program, okay? You send it through the Buds compiler, which produces SQL, and then you would feed that SQL into SimSQL, which would then iteratively run your computation, and you come back a week later, and then it spits out the answer.
So in particular, the SimSQL can run any database, including your PDB.
Well, okay, so actually this is a great question. I guess I wasn't clear. So SimSQL is a prototype database that we developed. And the reason that we developed it there was mostly because at the time that we started, and really to the extent the same thing holds now, there are no distributed databases available. And so that for open source, right? So we wanted to show that a database was a good computational platform for this sort of thing. The only option we had was to write our own, okay? So it's not necessarily that we think that SimSQL is the best database ever, right? But the reason we did that was that we needed a platform to do this stuff on top of, okay? Our goal on PDB is a little different. We are actually trying to make, in that case, the best analytics platform ever, okay? So it's not just a proof of concept.
But there would be a path from Buds programs to running on PDB, though.
Sure, exactly. So what we would do is you could either imagine an SQL to the C++ here, the translator, which actually wouldn't be that difficult because there's actually sort of these declarative queries within the C++, right? So we could glue that, yeah.
So you said for now you're using C++, and if you're successful, then what next?
Yeah, I don't know. I mean, I think we could have arguments about what that is, right?
Yeah.
So Java makes a lot of sense, right? But then a lot of the stuff we want to do gets harder with the JVM, right? And especially since, so Kia, postdoc who works with me, tells me that Java is getting rid of their unsafe library, which makes things really, really hard, you know, if you want to be really efficient. One that make a lot of sense with Python, right? Python is super popular for data science. Python plays really nicely with C++, right? It doesn't have this managed environment problem. So those would be the two obvious ways to go.
Okay, we are running out of time, so thank you, please, again.
Okay.
I have a couple of announcements for today. Since there was a Grace Hopper celebration, many students couldn't come, so we will circulate this video recording to all of them. And next week, we are going to have another colloquium, and the speaker will be Dan Wallach, another professor from Computer Science RISE. See you all then. Thank you.
No.